this set of Snap Circuits videos, we're looking at Project PC55 Electronic Cat PC up to Project 65, which is the Siren PC. So with Project PC55, our Electronic Cat PC, there it is in the book, and here it is on our board. So we have our oscillator circuit as before, using our two C2 and C1 capacitors, along with our 100 microfarad capacitor, providing some time delay on our NPN transistor here, along with our variable resistor and resistor here, kind of controlling both how the frequency is, but also the delay for how long the circuit can last. With, of course, the output from the oscillation going through our transformer and out to our speaker, with our press switch here to energize and de-energize the circuit. So let me go ahead and get Cam Studio going. Get our scope run. And we press our press switch down. You can see the waveform on our scope, and you can hear the tone coming out of our speaker there. And the circuit is staying live as long as I'm holding down the press switch. But with our variable resistor set all the way to the left there, this is how the tone sounds, and then when we release the press switch, our tone fades away there, and we can kind of see it on the scope as it fades out. And of course, if we adjust the variable resistor, we'll change both the waveform and also the sound or tone coming from our speaker. So we can hear when we get to about the middle there, we have kind of a high frequency sound, higher frequency, and of course more peaks there on our waveform. But then as we start going toward the right, it starts going back down in frequency, and as you can see from the waveform is changing quite a bit. Getting to a fairly low frequency now. Getting to where it's pulsing and it's actually slowing down to a stop. And now it's pretty much stopped. Until we bring the variable resistor back, it starts coming back up. And we see our waveform goes back to how we had it before. I can show this on our other scale a little more. And of course, if we have it on this side, it actually goes out pretty quick compared to this side here, where it actually lasts a little bit. So that's how Project PC55 is. Now 56, we're going to use our whistle chip and connect it between various points. So, and this is a funny thing too, it's another one of these little typos. Can anyone see something wrong with the picture here they have of the circuit? You can see where the connection points are, but in case you haven't spotted it yet, where is letter A on here? You have D, B, C, D. I think they meant to have A here instead of D. So if you see that mix-up, that's probably where the A is supposed to be. So anyway, we're going to connect our whistle chip across A and B, and then B and C, so pretty much across C2 here, and then across C and D, which will be across C1. And those will have the sound coming from our whistle chip here, but also it will change the frequency and oscillation of the circuit, because this also acts as a capacitor when it's in the circuit. So press the press switch down, and then we change it back to our 0.5 millisecond per division. So when we put it there, we can hear the tone from our whistle chip. It doesn't quite affect the waveform or the output of the circuit, because the capacitance there from the whistle chip doesn't really affect the circuit in that place very much. So that's how it is there. But now we're going to connect it across C2 here. And you hear that the circuit produces a lower tone and frequency, because with the capacitance there in parallel with C2, we're actually lowering the frequency of the circuit a little bit. And we can see that reflected in our scope there. If you look at the edge of the scope there, that one peak is showing. As soon as I put the whistle chip on there, it kind of goes away, so the circuit is going to have a slightly lower frequency. It's not oscillating as quick. Now let's put this in parallel with C1. And when we put it in parallel with C1, we have an even lower frequency on the circuit. As you see there, we have less peaks on the half millisecond per division. But let's see what happens with the circuit when we play around with the variable resistor. So there it is on kind of the other side. We still have that funny looking waveform and sound, but it has the same effect. Actually, it has the opposite effect, because you see the tone is lower there, but according to the scope, when we put this on, it actually goes up in frequency. So how about when it's in parallel with C2? Now when it's parallel with C2 here, it still goes to a lower frequency. And then like before, when it's across the transistor here, it doesn't affect it that much, we just get the audio. But it has the opposite effect across C1, where it actually makes it oscillate faster, versus the other way, where it makes it oscillate slower. So that's PC56. Let me bring this back over. So now, for PC57, we're going to take the speaker out of the circuit. And I don't know if this will work or not, we'll see. But we're going to use our whistle chip again here by itself, like we did in a previous video with a project, and put it across various points. However, because of the way that this cable seems to work, it may not work properly. So points A and B, so we'll put it across there. So our waveform is actually quite large, so I'm going to have to bring this scale down a ways. There. And you see we're kind of maxing out on the input of the computer right now, because the tips of the waveform there, positive and negative, are kind of flattening out. We can also see that fade out a little more on the scope here using just the whistle chip. Of course, we can see it on our 5 millisecond per division pretty well. So that's across points A and B across these transistors. So let's put it across C2 and see how it looks. And it looks a little different there. I need to adjust my trigger a little bit. But again, we're still getting some kind of flattening there. And we can see the fade out quite a bit, especially on our half millisecond per division. Of course, how does it behave with the variable resistor? See, it becomes a very square wave like there in the middle. And our waveform is very interesting looking there. So that's how it is there. Now let's put it across C1. Interestingly, no effect across C1. Putting it across C1. Surprisingly, gives us no effect. do have a little bit of effect coming from it, but it's not anything remotely continuous to generate a tone with. I think it's just got the electrical pulse coming through it. So let me put it back to here because we didn't try it on this side. Yeah, it's got very square wave-like properties there until we cross over to this side of the variable resistor. So that's project PC57. So now we're going to put the speaker back into the circuit. And for project PC58, it wants us to replace the 100 microfarad capacitor with the 470 microfarad capacitor, giving it more capacitance. Instead, I'm just going to take the 470 microfarad capacitor and put it in parallel here on top of the 100 microfarad capacitor, giving us 570 microfarads of capacitance. And of course, the effect is that the circuit is going to last longer when I release the press switch, because there's more stored energy there for the transistor to work with to stay active. So it will still fade out. It'll just take more time to fade out because there's more stored energy there with that 570 microfarads of capacitance. Let me energize the circuit, get this back over, and bring my scale back up here. Now when I release the press switch, you can hear that it just kind of winds out, because with more capacitance, there's more energy there to dissipate over time when I release the press switch. You know, of course, it allows us to see the waveform dissipate more on the scope. But as you can see there, the frequency or oscillation doesn't change. It's just the power output of the circuit goes away over time. So it's still oscillating at the same rate. It's just that it runs out of power to keep the transistor going. So that's project PC58. So now we're going to look at project PC59, which is the variable oscillator PC. So here we are with project PC59, the variable oscillator PC. Here it is in the book, and here it is on our board. So similar to our previous circuit, minus the delay in it, so we don't have the 100 microfarad capacitor here anywhere, but we still have our NPN transistor with our variable resistor, along with our R5 resistor and our two C1 and C2 capacitors that are feeding our transformer with our speaker on the output. So let me get Cam Studio going and power up the circuit. Now off the bat, the circuit does produce a lower tone / frequency than what we had in the Electronic Cat PC, which was PC55. And part of that has to do with the circuit arrangement here compared to what was in PC55. And we can see that reflected on our scope here, that it is a lower frequency / tone in our circuit because we don't have as many peaks here. And even with the variable resistor turned up, it's still a lower frequency in comparison. Now we don't have that funny waveform being produced like it was either in the previous projects, and again that has to do with how the circuit is set up here. Let's look at the 5 milliseconds perturbation. You can see what it looks like there. So that's how project PC59 works. So now with project PC60, we're going to take our whistle chip, and like with project PC55, we're going to put it in 3 different locations across our NPN transistor, across capacitor C2, and across capacitor C1. And of course, we'll get pretty much the same results as you'd expect when we did it in PC55. So we'll put it across our NPN transistor first. And we can hear the tone being generated by our whistle chip, but as we see from our scope, it doesn't really affect anything wise on the frequency or the amplitude of the circuit there, how much power it's outputting. You pretty much have just another form of audio being put out here by the whistle chip, so its capacitance doesn't really do anything right there. So now let's move it across capacitor C2. And when we do that, we lower the frequency of the circuit a little bit, because again we have the whistle chip's capacitance in parallel with capacitor C2 now. And by doing that, of course, again, as I say, we reduce the tone / frequency of the circuit by increasing the capacitance there. So that's how it is there. So now I'm going to put it across capacitor C1. And that one really does affect the circuit there, because again it makes it a lower tone, lower frequency, and you can see this reflected in the scope quite readily. So that's how Project PC60 works. And now I'm going to take the whistle chip out, and we're going to take our photoresistor here for Project PC61. So let's see. We're going to take our 100,000 ohm resistor out of the equation, and we're going to put the photoresistor in its place by letting us control the resistance using light. And of course that will affect the frequency of the circuit by depending on how much light we get in, and of course also depending on where our variable resistor is relative to that. So we turn the circuit on. Change to a ½ millisecond scale there. So now with the variable resistor where it is and the photoresistor, it sounds almost similar and looks similar to Project PC55 right now. That is until I start covering up the photoresistor, and with more and more resistance there, it now is making the frequency lower and lower until the circuit, with very little resistance, it's oscillating very slowly. In fact, we have to go to our 5 milliseconds per division to actually see these such low frequencies there. As you see, we got that funny waveform back when we used the photoresistor there. So you can really play around with the waveform here. So let's see. So that's how it is for Project PC61. So for PC62, we're going to remove the speaker. Now, it doesn't exactly say to remove the photoresistor, but I assume that it does want the photoresistor out of it and to be just like it was with the 100,000 ohm resistor. So I'm going to put that back for this. Take our speaker out of the equation. And this time we're going to use our whistle chip in the same 3 positions as before, but this time we're going to be looking at the scope. Let me get my B track here because it fell down. A, B, B, C, D, E. So I'll get our whistle chip connected up, and we'll put it across our NPN transistor and turn on. Let me readjust our scale. So that's where we have with our whistle chip looking like across our NPN transistor. Let's change the variable resistor. Again, we're flattening out on the top and bottom with the waveform there, again probably because of the computer's input. Giving it an almost square wave-like appearance there. Alright, let's try this now across capacitor C2. Again, the frequency is lower there. I don't see too much waveform change there with the variable resistor, but again, the overall tone of the circuit is lower. Again, just like what we were doing with Project PC60. But this time we're looking at it directly through the whistle chip without the speaker connected. Now let me look back at C1. And just like before with, let's see, I guess it was with PC60 and some of the previous ones, we can't see the effect there. Although that it's doing the same thing as we had problem with the previous project, because the PC interface cable itself appears to be affecting the operation of the circuit, so we can't really show that. We can show it in bits and blips, turning it on and off, although that gives us a distorted waveform. So that's basically it for Project PC62. So now we're going to move on to Project PC63, which is the Electronic Sound PC. So here we are, Project PC63, the Electronic Sound PC. Here it is in the book, and here it is on our board. So again, we have our typical oscillation circuit as usual with our NPN transistor, with our two C1 and C2 capacitors. This one is set up so that when we have our switch turned on, it's primarily just using our C1 capacitor to do the oscillation, and then with our press switch we can add our C2 capacitor in parallel with C1, and that will reduce the tone and frequency of the circuit, of course, by adding capacitance to it. So that we get our recording going. So when we power on the circuit, you can hear the tone coming out of the speaker and see our waveform here on the oscilloscope. We change it to 0.5 millisecond per division. That's what we look like here. So this is how the circuit behaves with just the C1 capacitor there. If I add C2 in parallel with it, you can see the change in our waveform, and you can hear that the circuit is producing a lower tone because it's going at a lower frequency. Go to our 0.5 millisecond per division, and you can see the difference quite readily on there between just C1 and C1 plus C2. So that's how Project PC63 works. Now Project PC64 has you change out the resistor, but they actually have a typo in the book here. They want you to change out this 100,000 ohm resistor and put the 10,000 ohm resistor in there, but see, there's a problem with that, because that's not where you're supposed to do it. You're supposed to change out the 5.1K resistor here, because you want to change it on the base of the transistor that's controlling the circuit, not what's across the resistor. So if I take something like my 100 ohm resistor and put it over top here to reduce the resistance, you see that our circuit there changes. So now we have different peaks there on our divisions, and if I use the press switch to add capacitance, again we get that same lowering of the frequency, but our waveform, of course, is quite a bit different. So that's the little typo with Project PC64, and that's how Project PC64 works. So now we're going to move on to the last project here, which is Project PC65, which is the Siren PC. So here we are, project PC65, the Siren PC. There it is, looking here, it is on our board. So we have a bit of an oscillation circuit with our NPN transistor and our C1 capacitor, but we also have a Darlington transistor set up because our PNP is helping to feed our NPN transistor here. Our 10 microfarad capacitor gets charged up when we press our press switch and limited by our R5 resistor, which helps feed us all when we release it. And of course we got our A1 antenna and 100 ohm resistors, which are helping to feed into our transformer and then output through our speaker. So let me get the oscilloscope recording. So when we turn the circuit on right now, nothing much happens because our 10 microfarad capacitor is discharged. But if we pulse, see, if we do that, we can charge up our 10 microfarad capacitor, and as we press that press switch on and off, we can charge it up more and more, and that will affect the amplitude, frequency, and stuff of the circuit there. So now it's starting to discharge, and it's discharged to a point to where we can see the oscillation happening again. And we look on our scope, we can see the waveform, and as that capacitor is discharging, the circuit is oscillating slower and slower, so going down in frequency, and we can see that as more and more of the peaks of the waveform go more toward the right on our scope. And so we end up with less and less peaks showing on the scope there as the frequency continues to drop, because it oscillates slower and slower as capacitor C3 here continues to discharge. Switch to our 5 milliseconds per division. And let's look at our FFT out of curiosity. Scale this up a ways. Well, there's not really a whole lot to see on it though. But let's go back. And again, if we want to re-energize that capacitor, we can just press and hold that for a second or two, and that'll bring the capacitor back up, and of course it'll bring the frequency in oscillation of the circuit back up to the point where we cut it off. And of course, turning off the circuit drains the capacitor pretty quick. So that is how project PC65 works, and that concludes this set of Snap Circuits projects. Only a few more left to go.